Well, hello all. My name is Stephen Thomas, and today we're going to be discussing the work-energy theorem, summarized by work-net equals kinetic energy final minus kinetic energy initial. And I thought, just to make it a little bit more practical, we're going to take one coin and a piece of chalk, and we're going to drop them, and let's see what is the final kinetic energy. If it falls from there to 1 meter down, how much kinetic energy will it have? Let's use the work-energy theorem to find that out. Now, many folks don't know that if you take something heavy like a coin, something light like a piece of chalk, and they think that if you drop them, the heavy thing falls fastest. But that's just not true, and it was proven by Galileo by dropping, I believe it was Galileo, by dropping a cannonball from the Leaning Tower of Pisa quite a long time ago, many hundreds of years ago. So what you could do is you could watch us dropping this piece of chalk and the 1 rand coin. We're going to drop them at the same time from the top of the board. They're going to come, there's 1 meter, I've marked it. And we're going to, you'll hear as it hits the desk below, it's going to make virtually one sound. Okay, on our marks, get set. You will, if you replay this and you use the full stop and the comma, you will see that both fell at exactly the same rate. And that is interesting because if you look at your equations of motion, which you could use to calculate what a 1 rand coin velocity would be after falling 1 meter, you could use, for example, that formula. But what you notice is there's no masses in any of the equation of motion formulae. You don't need the mass. Everything falls at the same velocity. Okay, so let's use, first of all, just to get some sort of benchmark, using our equation of motion, let us find out how much a 1 rand coin what its velocity should be after falling for 1 meter. So here's our V final squared equals V initial squared plus 2a delta y, where we've got our V initial equals 0. We've got our A equals 9,8. Let's have everything positive down, so positive 9,8. Delta y is going to be 1 meter. So let's plug in our values. V initial squared is going to be 0 squared plus 2 times 9,8 times delta y 1, so that comes to 2 times 9,8. 2 times 9.8 equals 19,6 is equal to V final squared. So V final is equal, if we take the square root of both of them, V final is equal to the square root of 19.6, and that comes to 4,43 meters per second down. So there is our benchmark for what we think the velocity of a 1 rand coin should be. So using our equation of motion, we're expecting V final to be equal to 4,43 meters per second. Let's write it down here. V final equals 4,43. Right, so let's get rid of this now and do it using the work-energy theorem. Now let's explain this work-energy theorem for you. the work-energy theorem says work net, the net amount of work done on, say, this coin, equals Ek final, kinetic energy final, minus kinetic energy initial. On your data sheet, it's sometimes shown as delta Ek, but that is the expanded or unpacked version of this. Net work is equal to a change of kinetic energy. So what is kinetic energy? Well, on your BFF or best physics friend, let's turn that here, you will see Ek is equal to a half mv squared. A half mv squared. Kinetic energy is energy of movement. So here, this thing's not moving, this coin, so it's got no kinetic energy, and after 1 meter, it is moving and it's got kinetic energy. Let's figure out how much kinetic energy it has. And let's put into this formula, we'll substitute Ek equals a half mv squared. So now we can say, going back to this, Ek final is a half mv final squared minus a half mv initial squared. Do you see that there we've expanded that to that, where because our kinetic energy formula is this. Right, so let's carry on. A half. Now what is the mass of the coin? The mass of a coin is 4 grams. The mass of a 1 rand coin, I looked it up on the internet, is 4 grams. What is V initial? Was started out at 0 meters per second. And what is work net? Well, there's our formula for work. Force times distance cos theta. So let's expand this as well. We're going to have, if we look at our diagram, there's only one force acting on a falling 1 rand coin. That is the force of its weight, or force of G if you like. So there's only one net force acting on an object, and we define a projectile as something having only one net force acting on. So let's substitute that in for net, work net. So if there were multiple forces, say there was an upward friction force, we would have to include that, but there aren't. So we put in here, work net equals force times delta x cos theta. Now let's get rid of the diagram. And what is the force that we're talking about? Here, it is the force of weight. In other words, force of mg, delta x. Now, what is our cos theta? First of all, we're going to use the mass of our 1 rand coin. Now, notice when you're using work-energy theorem, the mass becomes important, unlike when we use our equations of motion. So we're going to substitute in the mass 4 grams divided by 1,000 is going to be 0,004. We took 4 and we moved 1, 2, 3, divide by 1,000, times G, positive, G is positive 9,8. Everything happens downwards in this problem. So we say let down be positive times 9,8 times, now force and movement are in the same direction. The force of gravity is down and the coin moves down. So there's no angle between movement and force. So it's times cos of 0. Theta in this case is 0. There is no angle between the movement and the force of weight. Equals a half. Now let's get back to here. Times mass of the coin, 0,004 V final squared times V final squared minus a half mass V initial squared. Now V initial is 0, so I don't have space, but I could write half times 0,004 times 0 squared, but let's just say it's 0. It is 0. So, and this theta here should be 0. Right, so let's do the calculation here on this side. We got 0.004 times 9.8 times cos 0 equals 0, 392 equals a half. Let's do that calculation. 0.5 times 0.004, which comes to 2 times 10 to the 3 minus 3. V final squared. You can ignore the naught there. So to find V final squared, we're going to divide both sides by 2 times 10 to the minus 3. That cancels out and leaves us with V final squared. So let's say, going back to here, 0.0392 divided by the answer comes to 1,96 equals V final squared. Square rooting both sides, and we get the answer V final equals 4,43 meters per second. Now notice that is exactly the same answer as we got when we used our equations of motion. 4,43, using the work-energy theorem, it's also 4,43. So that is an example of how we could use our work-energy theorem. So what did we do, just to summarize it again? We say if you do work on a coin, it equals a change of kinetic energy. How do we work out the change of kinetic energy? Change of anything is final kinetic energy minus initial. Now, what is the work that is done? It's the work done by gravity on a certain mass in a certain direction. And that's what this formula gives us. Equals the final minus the initial. Now, the initial kinetic energy, it wasn't moving, is half m, where the v is naught, half mv squared is naught. So there's the work that was done. There was the final, there we're trying to find out the final velocity. We do our calculation, and there we come to our answer, which is giving us exactly the same answer as if we had worked it out using equations of motion, just to show you that the work-energy theorem does actually work.